Chapter 22 is one of the most difficult chapters in this class. Calculating the electric field, because the electric field is a vector, because charge is normally distributed in 3 dimensions, then calculating the electric field typically involves a 3-dimensional vector and an integral over 3-dimensional vectors. And so these vector integrals can become very, very involved. And so that has given rise to kind of a different way of looking at things. Chapter 23 introduces us to another way of looking at figuring the electric field and sort of calculating it backwards in an easier fashion. So this gives rise to some shortcuts that you're going to kind of appreciate. We start off, however, in order to get to that point, by defining something called electric flux. So what is electric flux? Well, the idea of electric flux comes from really the study of fluids. And so in fluids, you have a pipe and you've got water running down the pipe, and you often talk about the flow of the water in the pipe. And the flow of the water in the pipe is generally given by the volume per time, which is going to be the velocity times the area. Okay, and so when they started talking about electric fields, they decided to use a similar kind of concept. So if we've got an electric field and we've got an area over which the electric field goes through, they realize that, well, the bigger the area, the more field goes through it. And so they define something called the flux, the electric flux, and it's going to be the electric field times the area. So, for example, if you had a circle here and the electric field was going through it, okay, then that would be the flux. A bigger area, more electric field goes through. Or you could have the same flux if the electric field was weaker. And so this was the first step. Okay, but that's not the whole thing, because they realized if you tilt your area, then the electric field, well, there's actually less electric field going through it. So this also is related to the tilt. And so it's the cross-sectional area that matters. Okay, so that gave rise to the idea that the electric flux is going to be E times A times the cosine of how much it was tilted. So in other words, the side view right here. So, so side view, we've got this, okay, and then if we tilt it by 45 degrees, then less goes through. Okay, so that side view, top view. Okay, so I'm going to use the sort of way that we did this from Physics 1 for vectors. X means going into the screen, and so that would be looking from this direction. If I were to look from the other direction, so in other words, if I put my eye here looking that way, then it's coming at me, and so that would be dots right here. Now, I had a professor try to explain that to me once, saying, okay, we got a vector going this way, and imagine it's like an arrow here. We got feathers here. If you look from the back end, you see the feathers. If you look from the front end, then you see the arrowhead coming at you. Okay, and then when you look at the side, you just see the arrow. Okay, now, the electric flux is going to be EA cosine of the angle. Okay, so again, if I had a circle here, and we got the flux like that, okay, that'd be looking one way. So side view is like that. Okay, so my eye was right here, in the first example. Now, if I tilt it, okay, then I've tilted it by some angle theta. So we look at this, and we've seen something like that before. We saw that in chapter 3 when we talked about vector dot products. So that would suggest that the flux is going to be some E dot A. Okay, well, it's pretty clear the electric field vector. What is the A vector? Well, when it's oriented like that, then you get a lot of flux through there. But if you change the orientation this way, then none of the electric field is going through there. Here, the electric field is going through. In this case, the electric field is going past. Okay, so that would obviously be a theta of 0 degrees. You get the maximum amount through, and this is the minimum amount through, so that's going to be 90 degrees. Because this is going to be EA cosine of an angle. Okay, so that means that the A vector has to be perpendicular to the area. And in fact, that's how we define it. The area vector is perpendicular to the area. So if I imagine that I have a shoebox, then what's the A vector? Well, the A vector points away from each surface. So the A vector, the area vector, points away from the surface. Now, if it's a three-dimensional surface, then the area vector always points outwards. So that's our definition. Area vector points outwards from a surface. Whereas otherwise, it's just it's a little more difficult to figure out how we define it. Okay, if it's just a two-dimensional surface. But this is how we get the flux. So the flux, as I said, is going to be E dot A. Well, the next question is, what if we had an irregular shape and we have electric field going through this irregular shape? Okay, so the electric field is going through the irregular shape. Well, the flux, and the problem is that if the shape is irregular, then that means that the cosine of the angle is different at each little piece of the shape. Okay, it's also possible that the electric field might be stronger in one area than another area. So how do we deal with that? Well, what we do is we look at some little tiny bit of area, some little delta A right there. Okay, and so what we do is we say that the flux is going to be a sum over the E dot delta A's, and we're going to take a limit as the delta A's get really, really small. Well, what we've got here is a vector integral, E dot dA. Okay, so that, and what we often do is we put a symbol there in the middle of the integral to indicate it's integrating along a surface. So it's a surface integral. So we integrate around the surface, E dot dA. So this is our general form for defining electric flux. Now, it turns out, you're wondering, well, why do we bother with this whole defining of electric flux thing? Because that turns out to be a very useful concept, which we're about to apply in order to help figure out electric fields.